So we present a paper titled Novel Predictive-Coding-Inspired Variational Recurrent Neural Network Model for the Online Prediction and Recognition. The paper was published in the Neural Computation last year and first authored by the Ahmadi and myself co-authored Tani. I'd like to explain the motivation behind this study. So when we have a fluctuated spatial temporal pattern like this one, then it can be embedded in a deterministic model, deterministic chaos one side, but the other possibility is that it can be reconstructed in a finite, probabilistic finite state machine or stochastic dynamical system, like explained by the Langevin equation like this one. So we have two distinct theory groups, this one, but I'm quite interested in bridging the gap between these two extremes way of thinking by examining predictive-coding type framework, especially as implemented in a recurrent neural network model. Now, I like to provide an intuitive explanation about the predictive coding, and this is a hierarchically organized neural network. We have a prior belief in the beginning, and it is going to have the top-down pathway and predicting for the both exteroception, the vision, and the perception. So prediction, the perception means that almost like predicting the next joint angle in the case of the robot, and that one is fed into the controller, and the necessary motor torque is computed, and that one is act on the environment and causing a state transition in the environment and generating new sensation. So the both exteroception and perception. If there is error between the predicted sensation and the actual one, the error is going to bottom up. While error is bottom upping, and then in the prior state at each layer is updated to the posterior value. Finally, the prior belief is updated posterior with the optimal values. So this is a predictive coding and active inference framework. So now I'd like to explain more specifically about our proposed model, Predictive-Coding-Inspired Variational-based Recurrent Neural Network model. So in this model, we're going to maximize something called the lower bound. The lower bound consists of accuracy term and complexity term. So we have to maximize the accuracy, that is minimizing the reconstruction error, and also minimize the complexity in terms of KL divergence between the posterior and prior things. So, and we have something called meta prior, that is a parameter of the weighting of this complexity term. So, then this is a graphical model, and this is a time step and time processing. And then we have first is a probabilistic latent variable for each step, that is the prior and posterior things. And then we have a deterministic latent variable for each step. And then we have a prediction of sensory sequences. So they're using both probabilistic latent variable added to the deterministic latent variable, the prediction sensory sequence is generated. Then now we have the and also and prior is represented by the Gaussian distribution like this one for each step, actually by the mean and sigma like this one. So then we have the target observation. The day and sensory observation comes. Then if there is error between, the error is backpropagating through the time from the backward manner. When the error coming to this posterior, and the posterior value is updated by using in the direction of minimizing this error. So, and then we have posterior inference for each step. So actually, in the attempt of the maximize the lower bound, that we do a iterative computation, and through iterative computation, posterior distribution is optimized. Additionally, I note that the KL divergence can be computed analytically. Now, I like to explain the learning process, especially the PV-RNN implemented at multiple levels. So the PV-RNN has a fast dynamics layer, the intermediate dynamics layer, and the slow dynamics layer. So time scale of each neurodynamics is characterized by the time constant tau, shown in this neural activation dynamics equation. So then the top-down prediction process starts from the higher level, and then it propagates downward manner, and through the time step is going like this way. So that is a forward of computation. Then we have a sensory observation here, and then if we have the error propagates bottom-up manner from the lower level to the higher level, and then propagate backward in a time step, like this one. Then actually when the error comes to the posterior, then posterior is updated. All posterior in all layer, all steps is updated. So actually learning the process is update both synaptic weights and the posterior for the purpose of the maximizing the lower bound. That is learning process. So after the learning and synaptic weight is fixed, we do the prediction and the post-prediction online manner. So this is a past window, and this is a future window. Now is here. Then we have a reconstruction of the sensation, observed sensation, and then if we have the error propagating, and then that's going to update to the posterior for each step for each layer. So this is reflecting the past, and then we can confirm the latent variable of the current time. Based on this confirmation, future multiple steps look at the prediction can be done. Then we're gonna have the time one step shifted like this one. So then we do the same things for this new past window, error regression window, the future window of this one. So in order to perform the experiments of the learning and the PV-RNN, we use a 2D hand drawing pattern collected by the volunteer students. So we ask the students to draw hand drawing primitive movement patterns. Then that movement pattern is switched, and by throwing probabilistic finite state machine like this one. So then first is drawing the circle 3 cycles, followed by figure 8 3 cycles, and then followed by again by the circles, and then go to the 70% figure 8, 30% the inverse triangle like this one. As a result, we can get drawing 2D hand drawing like this one. So this is used for the training. So actually, we're gonna get 400 steps for each sequence, and then we collect 16 sequences. So that's generated by this student. And then the PV-RNN was trained using this training data, but with using different value of the metaflyer W. So as I said that the network is trained with different metaflyer W of this one. And then now we look at the construction of a specific target sequence pattern used for the training, how it's going to be reconstructed for each network use different W, trained with different W. So then what we see is that this is a target used for the one with the target used for training, and then this is a reconstructed one with a different W. So in case of the W is 1.0, very large, we see that this one almost same until this one. Really nice reconstruction, very good reconstruction. So then the W is increased, the up to here in this case is okay, but after that one, this one is not so, is broken. So then is the further W is increased, and only reconstructed well up to here, and the final W is set to 1.0. It cannot be reconstructed at all. So what we see is that in the case of the W is 1.0, we see that the sigma is developed for each step almost zero. That means that the deterministic dynamical system is developed in this case. Actually, the Lyapunov's exponent becomes positive. That means that the chaos is generated in the case of the training with W equals 1.0. So, and then in the case of W equals 0.1, it's going to be the random process is developed with a sigma for each step to become a very large value. So the optimum best reconstruction actually comes to the W is 1.0. Look at the generalization capability of the trained network by examining the predictability for the unlearned test sequence pattern. So this is the unlearned test sequence pattern. The network is going to observe the temporal pattern up to here, so around 200 steps, and the network is trying to reconstruct by updating posterior for this observed sequence. Then try to predict for the future of this one. Try to predict for this one. So then in the case of the W equal 1.0, the network trained with W 1.0, and so this both reconstruction and look at the prediction is not good. It cannot be reconstructed very well. And then when the W is decreased, and then what we see that around here, W is 0.25, we see that a very good reconstruction of the past, also future prediction is very good between this one, so target and this one. And it is saying that BA, CAB, that is actually following this finite state, provides finite state machine. And then that means that this network is actually extracting grammatical structure hidden in the data. So, but if we then we look at further reducing the W like this one, then the construction here is okay. So, however, its kind of prediction future is not so good. So therefore, best predictability comes to the intermediate region. The W is set to 0.25, where we see the best realization. So then so this is a summary of the prediction performance. And then, so this is in case of W is set to 0.25, the one primitive ahead prediction capability is 100%, very good compared to the other. The even two primitive ahead prediction, that is 84%, that's very good compared to the other. Even it can do the three primitive ahead predictions, the best perform in the case of 0.25. So now I'd like to explain the why with a small W, the probabilistic dynamics is developed and the larger W deterministic dynamics come. So let's think about probabilistic state machine like this one, simple one. So state 1, state 2 are deterministic transitions. State 3 is a probabilistic state transition. So let's look at the small W case. Then in the state 1, state 2, so we have a sigma and prior and posterior is quite both a narrow sigma is quite similar distribution. Same for the state 2 transition. So this is deterministic. So it's so that is because transition in this one and this one is going to be deterministic. So therefore this is okay. So however, the state 3 is going to be different. So we have a wider sigma in the prior. So then that is because posterior could be either this one or this one, depends on whether you go this way or this way. So then the prior cannot predict whether this one comes, this one comes. That's why it's going to be the wider sigma comes. This wider sigma is allowed. So these prior and posterior is different distribution. That is allowed because very small w. That is less constraint for the K divergence. So then this wider sigma is going to be the source for the generating probabilistic dynamics. However, in case of larger W, the situation is going to be different. So state 1, state 2 transition, that is the same. However, state 3, so we will have a distinct distribution. The two cases possible. So that is both are narrow sigma. So then it's going to be the posterior is going to be the coupled to if this appears, then this appears. This one is going to be, and this one is coupled. So why this goes in this way? So again, posterior is going to be the narrow because in order to make error minimizing, and then if this comes, and then this is also should be narrow, and they're going to be have the same similar distribution because of the large W. So that's why in prior is going to be the very narrow sigma. So then that is deterministic dynamics generated. Whether this one comes is depend on initial states. The deterministic chaos generated, and either this one or this one comes with a small difference of the initial state. So in this way, deterministic chaos is developed. Now I like to summarize what we have seen so far. So now we're changing the W. So with the prior, that is constraining the complexity term. Then if we change the method W, so meta prior W, and in the case of the larger case, the fracture temporal pattern is embedded in deterministic chaos, but the W is small, so then it's embedded in the stochastic dynamics. We are making the W's larger, and the strong top-down prior with a high precision is developed, and then that leads to the road running by overfitting. And on the other hand, if we set the small, we're going to have the weaker top-down prior, the low precision, and then it goes to the random process. So what we found is that in the intermediate region between these two extremes, the most generalization can be seen in this region. The further we speculated that the case of the ASD might be related to this region of a mechanism. So as like these researchers are saying, like hyper precision and the road running. So those things might be very much analogous to the ASD case. I like to show the comparison between the PV-RNN and the other type of variation recurrent network, VRNN, developed by the Chung and his colleague. So, and the PV-RNN is, as I explained, a posterior inference is conducted by the error regression. So using error signal is updated in posterior. So, but in case of the VRNN, in a much simpler mechanism, that is input is fed into the network. So then it's going to, the latent state is inferred. Then prediction is made. So in order to compare these two network performance, this robot was trained to generate for movement pattern by imitation of a demonstrator robot of this one. So after the learning and during the test phase, when the pattern demonstrated by this robot is switched from the one to another, actually this demonstrator robot is manipulated by the experimenter, and then this imitator robot should follow it by the inferring the switching happens, that inferring the latent state, current state. So that is the inference of latent state is done by the either the error regression or input entrainment in the case of VRNN. So we're going to compare it. like to show the comparison between VRN and the PV-RNN. So this is showing the mean square error between the target and look at the prediction of defined steps and all different steps. So PV-RN mean square error is much smaller than VRN. So now we go robot demonstration. So this is a target, and the PV-RNN robot and the VRNN robot is following imitation. So when target switches the pattern, now switch, but A is not doing so well. So, but he is doing very good. And then now switched again. This time the both are doing good. Again, switch, but he's not doing it. Kind of confusing. So we showed it's shown that PV-RNN robot is much better than VRN. Okay. So now I'd like to show the summary of the current study. What we have shown is that the current study proposed novel variational-based recurrent neural network model under predictive coding framework. The next is that it was found that the regularization of complexity term in the evidence lower bound affects the network characteristics very significantly. So then with a weaker regularization with a larger W leads to the development of a more determinist dynamics with a stronger belief. On the other hand, stronger regularization with a smaller W leads to development of a more stochastic random dynamics with a weaker belief. And eventually, the best generalization in learning can be found in the intermediate range between these two extremes. Finally, we have shown that the PV-RNN using the error regression scheme for the inference outperformed VRNN using the input entrainment, as we have shown in the video. In the last, I like to introduce recent developments using the PV-RNN. So this paper introduce how the PV-RNN can be applied to the human-robot imitative interaction using pixel-level vision. And this paper is going to introduce how the goal direct planning can be implemented by using the PV-RNN. So this is the end of my presentation, and thank you very much.